So, welcome to my talk on AI/ML models for mobile devices. This is a short discussion on some of the works that we have been doing at Microsoft India Development Center. And the main aim of the talk is to give a breadth-wise view of the main challenges and the opportunities that come when developing AI/ML solutions for mobile devices. And some of the solutions have, in fact, as we will see, have been integrated in the Microsoft 365 app. So what are the real world challenges? What are the constraints that are that actually come both from ML design engineering as well as from a business perspective, right? So as it's clear that smartphones have become ubiquitous computing devices, and they are the go-to devices for capturing content and for sharing content, right? And so the mobile devices, since it's resource constraint, so the usual AI/ML architectures which are discussed, the large scale architectures, those are won't be feasible from a user perspective. I mean, so both from a point of view of limited memory or storage or processing power, battery life, or the latency at which the user should get the output, those are not sometimes feasible, right? And in this talk, the main focus of the models will be to get a simple get a capture of the documents on smartphones in a very simple and effortless way, so that there is an automatic information extraction that can happen. There is a ease of sharing, and the models are on device. So by on device, I mean what I mean is that the data does not leave the user's devices, so that there is a complete respect of privacy and protection of user data. So let me begin with a demo of the deep scan feature, which was developed by our group and is a part of Microsoft 365 app. There are several ML building blocks which are required, which I will go in the rest of the presentation. So there is a voice here. So it's
scan the photo of a book page and open an existing photo which has text.
So you can scan a photo and you can click it. If you click it, then the text from the image is selected, is identified, the text regions, which you can then use in some downstream application. You can translate it, and all those pipelines are there. You can create, you can paste it in your new PowerPoint presentation on the fly. And the more difficult part is to extract the image. And here you want to extract a very crisp boundary so that it can be used directly. It should not have a lot of background.
Open your slide or document to paste it there, and you will find a very clean and high quality pages ready in no time. Extracting information from images has never been this easy. Simply scan.
So as you can see, this simple demo required a lot of basic ML building blocks. So what are they? So let's say I capture a photo of an image, a photo of a document. So it's a children's book, and then the first step which happens is basically you want to identify whether the image has a document or not. So the first, among other things, the document image classifier will say that yes, there is a document which is present, and it should happen in real time, because as soon as this thing happens, the document is identified. So the quad detection algorithm comes in, and it will identify the 4 points of the document and basically the quad boundary, and then a host of document image cleanup algorithms will come in, which will do perspective correction. It will do some kind of foreground enhancement, a lot of background noise removal will happen. These are all happening in background, and it will happen, it should happen in a very real time for the user to actually use it. Otherwise, for each step, if it is taking 30 seconds or even 5 seconds, then it is, I mean, nobody will be using it, right? So after these two blocks, then the region segmentation comes in, which identifies what is the text region and what is the image region of the document. So when you have the image region, again, it can be extracted in a very, with a very crisp boundary, which can be subsequently used. And the OCR can then, OCR as well as other NLP blocks can then work on the text region to let's say do some semantic search or use it in, do a translation or any other thing, right? So this is the kind of different ML building blocks which were triggered in this whole demo which was done. So in this today's presentation, I will be covering, I mean, at a very shallow level, the basic ML building blocks of the document image pipeline, understanding pipeline, as well as another important problem, which is generating or obtaining real data. And this is especially a very important and hard task in industry setting, because you have to again respect several constraints. So we'll get to that. And I will also focus a bit on other interesting problems on devices, which are like semantic search with text or prototype selection, if the time permits. So coming to document, so let's begin with document image classification on a mobile. So why is this required? So document image classification is required, and it because as soon as a document is like presented in front of the camera, you should be the pipeline should immediately identify what kind of image is there, so that the next scenarios can be triggered. So if, for example, a receipt is there, is shown, then the next one of the pipelines that one of the scenarios that which could be triggered is that you could ask the app to convert it into an Excel sheet, which will extract all the information like vendor or the items which were used, the total amount, the address, all those things, and put it into an Excel sheet. The information is directly extracted. Or as we saw in the demo, if it is a news article or something, deep scan can be shown as the possible scenario where the image and the text information is extracted. If it is a form, it's a filled form, then the obvious scenarios could be to recognize what kind of form is there and then extract the relevant fields which are filled in the form. So bank form could be different from like a health hospital form, right? So all these things could be triggered as soon as the classification is done. Or let's say if there is no document, right, and it's just a natural photo, then what kind of image enhancement filter should kick in if it's a natural image. So these are like the kind of different scenarios that are triggered as soon as document classification is kicked in and the output is obtained from there. And one of the things which is with the document image classification is that it is actually most of the time it may not be an end-to-end scenario in itself. It is a part of the whole pipeline in which the document classification comes in maybe at the start or in the middle, right? So the classifier specifications, like how big the classifier should be, or at what rates the classification should happen, what is the latency, all those things would vary. So for example, in the scenario that I just now showed, where we need to classify whether a given image has a document or not. So for that, the next, so again, that is not a end scenario, because it is required to decide whether the quad detection should kick in or not. So a lightweight, so we had developed, for example, a lightweight CNN based model, and its latency should be real time. It should be like greater than 80 frames per second. So it should be classifying in that thing. And the model size should be typically under 200 KB. So I mean, usually when we, in the research papers, sometimes when I used to study, at least it's a small model, then the size could be like 10 MB or so. But when we work in business environment, then the size of small actually changes, and we have to fight for like 10 KBs with the business team to convince them that this 10 KB is really good for the users, right? So the war does not happen on, or the battle does not happen on MBs, it is on KBs, right? So this is like one scenario which is there. And so the other kind of classifications that can happen is, let's say there is a predefined taxonomy, right? Predefined categories. So for example, if it is receipts, then is it a invoice or a handwritten receipt or digital receipts, which is like the UPI receipts. And again, based on the classification, some particular different processing can happen. So the main question then comes, how are they related to each other, and can the classifier make use of the relationship between the two? And again, a very important problem which I will come in the later discuss in the later part of the presentation is obtaining supervised data. This is really painful in many settings, because in academic settings, many of the data sets can be just used to show results, it can be published, but in industry, we have to respect various compliances and user privacy while building such models, right? And the other scenario could be, let's say, I mean the classes could be defined by the customers also in many cases. Let's say there is a bank scenario in which the scenario is that a new kind of form is started by the bank, and it just shows 5 or 6 new, I mean that kind of form, and the classifier should basically understand, okay, this is a new class and I should be categorizing this as a 6th or a 7th class from now on, right? So in such cases, again, you don't have any understanding of the training data, because it's there with the user. We don't have the data at this stage. So some kind of a nearest prototype classifier, a very lightweight KNN model can be used, and so on, right? Yeah. So see, again, classifier is, as I said, it's not an end goal. So if classifier would have been an end goal for a customer which was important for the business, which will be creating revenue, then obviously a larger capacity would be set aside. But the end, for example, this demo, it's a part of Microsoft 365 app. So the end goal, I mean, so it has several purposes. It's not just classification. So there are several components which will be taking up delta size. So overall app size will already be somewhere around 80 to 100 MB. Yes. So that app will be multi-purpose. I mean, scan is just one of the features there, and in the scan, classification is one of the sub features there. So the quota becomes smaller and smaller as you go there, right? So this is the classification. So again, in the talk, I will be not discussing in detail the solutions, but what are the main challenges and the main problems that are faced, that we face. So now coming to the quad detection scenario. So detecting the boundary of the image which is being shown, the document image. So what is the scenario? The user should be able to scan the document with arbitrary background and effects, right? So scan should identify the document boundary, it should do the perspective correction, and all this should happen again in real time. slightly lesser than in classification, because that is the first thing. There the camera is actually on when you are doing the classification. Here at least you have captured it. So, or still many times the camera is still on, but it is slightly lesser than that. And here again the model size is 600 KB or so. So again there are several solutions which have been explored in the literature, but the focus on mobile devices is like very less. We get very nice solutions with large scale architectures and all, but the main challenge is to come up with a small scale solution which is good enough from a business point of view. So again, I will just show one of the scenarios, again one of my kids' books. So this is the photo which gets captured by the mobile, right? And now the quad is getting detected here. And now the perspective correction and all those things happen, and this is the final image that you get, right? So this is the overall scenario. And again, quad detection is again a whole lot of algorithms have been proposed here. There are like the basic components include edge detection, edge linking, then like several quads are possible. So you have to create those and like do a ranking, and then suggest the one which has the which suits the best, which has the highest relevance, right? So in each of them there are statistical methods as well as AI/ML methods. I won't be going into the detail, but these can be searched, I mean, later. Now coming to document image cleanup. So this is the third part. So first was classifier, then the quad got detected, then the image is now cleaned up, right? So this again is important because real world documents itself, they get spoiled maybe due to aging or stains or ink spills, right? So when we capture them, those noise gets automatically integrated into the document image. And even if the document does not have any such artifacts, there could be like shadow or non-uniform lightning effects, right? So if it is a whiteboard and there is a tube light which is opposite to it, if you take a capture, then it will be shining. So that part, so some part of the whiteboard won't get captured, right? And why such removal is important? Because A, it impacts the readability of the digital documents, and B, it also breaks down the document image pipeline. So I mean this document image cleanup can be an end goal in itself, but if the output from here is then given to a downstream application, then those applications can break. So for example, the OCR may not be able to detect some characters because there was some ink spill there, right? So just to give an example, this is the input, and in this input the noise present should be removed, which means that the background region should be detected. So the foreground contains usually the information, and the background is all those light orange kind of color. So first problem is to identify those pixels and then remove the noise from there. And similarly, the foreground pixels, they again should be identified and they should be enhanced for better readability, right? And then you can perhaps give two versions of the output. I mean, again, it depends from application to application. What is the scenario? You can either give a color output or you can give a binary output in case you just want to read the document and have some compression, because binary images will have a very less storage compared to the colored ones, right? There could be a grayscale in between, right? So what are the challenges here? So the challenges include bleed through. So by bleed through, I mean in the first receipt image, the background, some of the portion, I mean the back of the image is getting shown because the paper quality is very, very thin, right? So it usually happens when we get a receipt on those very thin papers. right? So when we get the thing, the thing which is printed on the back is also captured, right? Or there could be some reflections or lighting effect. The paper texture, for example, in the second, there is some paper texture, so those lines are coming. These lines can be taken as maybe lines of a table, maybe perhaps in the downstream application, or there could be other things, right? So these are like some challenges. The other challenge is what is the foreground and what is the background. So here we can see that, okay, background is the blue colored thing and foreground is the black color thing, right, which is there. But if we see it in the context of a bigger picture, then things may change. Now the whole thing which is in that mobile is the foreground, right, and the text is also the foreground, and the A4 paper is kind of the background on which it's being printed. So things, I mean, such identification is challenging. Then there is some inversion of color which happens. So usually mainly the white color, I mean light colored background is usually present on printed documents, and on that the dark colored text is present usually. But it could happen that there is a dark color background on which a light colored text is present. And this could happen simultaneously. Some part of the document has this thing, other part has something else. And these are like real life instances, it's not generated artificially, right? And then there could be, so one other challenge is obtaining good quality supervised data, because if we are training a supervised algorithm, then we should show the algorithm, right? What is actually a clean image. So cleaning that image pixel by pixel, let's say via some software, is very hard, and even then doing it manually may not result in a perfect thing. So here, for example, some of the things are from those network is like very lightly shaded. So these kind of noises are always there. And then on top of such challenges, there is another challenge of device side inference. So again, a good enough latency, I mean a low enough latency, model size again low in KBs, in few hundred KBs, and low energy consumption, which essentially means that the number of multi-add operations should be minimal. So all these things, for example, if you use any DL, I mean CNN based models, they will require matrix vector multiplication, right? So the number of such operations should be minimized. So the network design should be such that they are as low as possible. So in cleanup setting, there are a few algorithms which are completely statistical. They don't have, so to say, quote unquote, the ML component. What they will do, they will break the images into patches, and each patch they will identify, okay, this is a threshold. So below a threshold, if a pixel has a color below a threshold, then it is assigned to a background. If it is above a threshold, it is assigned a foreground pixel, I mean classification. And this is done at various level. You can do it pixel wise also, you can do it in blocks also. So these are called adaptive methods in general. Sovola's algorithm is a very popular algorithm in this domain. And we'll see what are some of the issues here. So the issue is that when there is a fixed set of information here, the threshold, then sometimes the foreground information is lost. So when we just blindly apply the threshold at different patches. So however good such algorithms may be. So we can see that the information is lost here when we do this kind of cleanup using adaptive algorithm. So we had recently worked on this kind of approach. So a main advantage of such approach is that it's very, very lightweight. Since it's statistical, so it's very lightweight, it can run very fast. So we have tried to see how to maximize the foreground preservation, I mean in the Sovola setting only. So another such example could be where Sovola's algorithm, for instance, loses information is primarily in images. So how can we preserve most of the information? This is one example, one of my colleagues' son, he had some homework assignment, and which he tried to capture and share via mobile. So if you use some standard algorithm, then there could be a loss. So even here there is a loss, but it's less lossy, so to say. But again, there are challenges. No algorithm is foolproof, so to say. And so these are so the adaptive approaches were unsupervised. They were purely statistical. Then there is another class of algorithms which are supervised approaches, which will use the neural network, so to say, and other techniques. But again, a very less focus is on very small scale solutions, again of the order of few hundred KBs. So we had worked on this problem last year for the overall scenario, and we had developed a lightweight document classifier with perceptual loss. So the perceptual loss, what it does is it will try to take the loss at some high dimensional feature, maybe from some layer of inceptions network or so, and it will try to do this. So overall, the size of the network does not blow up, and the output quality is quite reasonable. So again, we need to understand that at 300 or 400 KB, we won't be getting a very good output of all kind of images, right? There will always be trade-off. It's not that at 300 KB we are solving everything, and no size is required beyond that. It's all about the overall business objective and how we are able to satisfy that given the constraints, right? So this, and just to give an idea of the properties with respect to something like DE-GAN, which at least was the state of the art perhaps a year ago, there are several X reduction in size. So for example, from 121 MB, we go to something like 500 KB. So there is no trick, so to say. So one of the main thing is to satisfy the constraint. So the constraint of, let's say, 300 KB or 400 KB, which is defined by the business team. And in that, what could be the best solution that can be achievable? So, sorry? That is the problem statement. So the solution, so this was like one of the solutions. So this is the network that we had proposed. So it is an encoder-decoder based network. So okay, so the aim of this thing was not to give solution, but to show the different problems. So that is why I did not concentrate much on solutions. I'm just giving a flavor of what all things are there. So it's basically an encoder-decoder based model where we try to capture the overall image in some CNN based features. We use ResNet blocks. So larger networks will use more bigger encoder. So the stacking, because that will give you better and better output. So even with 300 KB, so for example, let me just show you some examples. So here it will come. So for example, some of the so even with the proposed approach, we will be getting some noise which we are not able to remove. So that will always happen. But the aim is to get as best model as possible, satisfying the device constraint. So main engineering will be the data set curation. So that is a very big issue that we face for real life thing. So usually in academia, when works are published, they are shown on some standard data sets. I mean, even this is a very standard data set. But the next one, it's like our own data set. So getting a clean image of such things on real life example, this is a very big challenge. And to do it, obtaining this data set, and one of the things that we had observed is that very less in general exploration has been done on device side. So so for example, when we started the problem and if we wanted to know from literature, okay, what is the best thing which is possible to do in 300 KB size? I could not get a paper. It could be a very general, simple thing, no novel thing. It's just that these things can be carried out, and in them, this looks very nice. So even this standard thing does not exist. Perhaps because it's a very mundane problem for for the academia. So overall, I was just saying that so in terms of properties, we want, for example, very low latency. So here per patch size of different of existing models, they take around 0.36 seconds. So for 100 patch image, it could take somewhere around half a minute to quarter of a minute. I mean 3/4 of a minute, and user will not be waiting for that much time. User will not wait for a minute to just clean up. You have to give it very quickly. So something around 5 seconds, 7 seconds, 10 seconds may be something reasonably good. Yeah.
Those are two independent attributes. Right?
Yes.
Lots more memory and give a fast.
Yes. So yes, but in our setting, we needed to reduce in everything. We needed to cut on operations also, in size also, and as well as low latency. So there is no trade-off, so to say. Yeah.
And what about like the other examples of cleanup that you showed? Were like in some there was this normal noise removal, in some
Yes.
background, foreground,
Yes.
classification, etc.
Yes.
So how does the pipeline kind of understand what kind of operations? Because
Huh.
operations are pretty simple to do steadily.
Yes.
The only thing that needs to be automated is what kind of operations should be done to what conditions.
So there is no one size fit all in this case. So different kind of noises will require different kind of cleanup method, and many a time the user is like provided an option with an array. We also have a classifier to determine which is the filter which best fits this thing, but that is again governed by business needs. So for example, there could be a business need that the classification, I mean the cleanup of whiteboard should be very good, because some particular customer wants that to be automatically be extracted the content and shown in let's say some PPT. So in that case, that specific business decision will be integrated into the pipeline of classification, and the classifier that can be a default there could be some classifier which does nicely on whiteboards, but not so nicely on other images. Yes. Yes.
But then the original pipeline that you showed,
Huh.
cleanup was one of the parts.
Yes.
The actual tasks of OCR and
Yes.
so in that case, that would kind of need to be automated.
So there in those settings, so if there is no specific thing, then there is a very standard thing that is being done, which ensures that there is no loss of information. So in these such DNN based models, so since it is a just a second. So this DNN based model, it's an image to image translation. So there is a chance that for certain kind of images there is a loss of foreground information, a high loss. So when there is such a automation which is there, then we try to use a model where the loss of information is minimal, because even if some noise is present, if the original noise, that is still fine, but if we add some more thing by removing some of the foreground information, that is definitely not a very good thing to do.
That's understood. Just one other like idea, like what if, I mean, the original this is to separate different classes of documents.
Yes.
Noise of the problems in it. And then since we are focusing on areas in one big line, what if we could use some kind of like self-supervised clustering method to classify objects as to what operations need to be done on them, and then do those operation statistics? That's some kind of approach that would be feasible in Edge, or is that too
Okay, so we technically we did not apply that this thing, because many of these problem statements they come they have some kind of a structure. It's not like a open ended problem like we have to develop a classifier and we want to develop in however way. There is some guidance from the business, right? So that self supervision can come in perhaps where the customer, for example, can create a new classes or have an option to create a new class. There for in that bank scenario where the bank introduces a new form, and so the bank can show maybe 4 or 5 forms via this mobile cam and ask, okay, so this is my new class, now you do whatever you want to do. In such cases maybe that thing can be implemented. For yes, I mean in the standard setting we don't want to specialize anything for which is suited for one specific scenario. Yes. Thanks. So these are again some of the outputs, the color outputs which we had obtained. Just showing, I mean these black things are just removing some personal data from this thing. Now coming to the image segmentation model of which the demo was shown. So what exactly is image segmentation problem? So in image segmentation we want to segment the document image into some semantic structure. So what is a paragraph? So a paragraph should be identified, a table should be identified, where is a figure which should be identified. If there is a, I mean, you can do very fine grained structuring like a caption, a list, things like that, right? And it is technically a multi-class problem, but multi-class has its own set of challenges. Yeah, and its applications include extraction of semantic structure like tables, figures, paragraphs. It could be used in downstream applications where we want to do cleanup based on some specific region. So image region will have a different algorithm, text region will have a different algorithm for cleanup, table region can have a different algorithm for cleanup, right? And there have been other usage in the literature, for example, for information retrieval or for converting unstructured medical documents into clinical reports. There have been some exploration in this direction also. And so one of the, I mean, some of the directions of explorations has been different kind of loss functions to predict the image boundary very crisply. So that is a very important problem here. We don't want a figure which is extracted with a lot of background boundary, right? So and different architectures have also been explored here. And again, as I said, we need a very crisp extraction. So I mean, there can be many different varieties of documents, right? And it should work on a large variety of documents. So this is, for example, the output of that model that we have discussed. So again, this works on some specific kind of documents that we have trained on. It will again not work on a very general class of documents. And the main challenges again include the multi-class, I mean getting a multi-class data set. So in order to train such models, we need such outputs. So one needs to then again manually tag such regions in order to make the network understand, okay, this is a table and this is a figure, or this is a paragraph region, and so on, right? And again, latency, size, minimal, multad, so all those standard mobile site settings are there. Now coming to generating or obtaining document. So as I said, obtaining supervised data is like very critical for such algorithms, because the size is very small, so you want to work on good data, but obtaining the gold standard data set is hard. And why it is more challenging in industrial setting is to ensure, because we need to have the ensure the compliance. that we are not taking any customer data without permission. And even if we take customer data, it needs to be trained in an eyes-off manner. By eyes-off manner, we mean we cannot see the input data, we cannot see its output. It is just fed to the algorithm automatically, that's it, if the permission is given. Then there are certain public domain data sets where whose commercial usage is not allowed. So again, that is a big issue, right? And then there are certain scenarios which may be important from a business perspective, but its data set is not available, right? Because for instance, ImageNet data will not solve every problem which is coming in the right. So, and again obtaining, I mean this is needless to say, but obtaining high quality label data set is costly. So again there are these budget constraints which are there. So one of the typical solutions is to have something like a Blender pipeline. So what does it, so what do we do, so let's say for quad detection algorithm, how can we generate the data? What we do is we collect some number of foreground images, some number of background images, and we try to overlap one over the other with the different perturbations. So the perturbation could be something like a field of view perturbation. So we need to generate an image when viewed in this way or from that way, or some lighting effect is there. We can introduce, let's say, some crumpling effect, right? And the main, the good thing is that the original, I mean the noisy input as well as the clean output is available. So we have this parallel data which we require, and yeah, and in this way we can generate lots of data for, let's say, quad correction. So this is like some examples that we generated. So we can, I've just marked 2 examples which were generated with the same foreground and background, but they are completely, they look very different because of the different style of noise which was added. Then another parallel approach that we had recently done as a part of Microsoft Academic Partnership Grant is we tried to generate realistic noisy images and the corresponding ground truth using GANs. So we designed a self-supervised system where which can technically generate handwritten texts and with different writers. So writers are fixed. So we had, for example, 120 or 150 writers whose handwritings we had access. I mean, we had access to. So different style of handwritings can be incorporated in this network, and it can generate like struck out text or with variable background and text in different languages. And but the key thing is that it gives us both text labels as well as pixel level annotation. So that is the main thing, right? And what can be done? So in this work, what we did was we used this artificially generated data to fine tune a OCR model, and we obtained a significant improvement in the OCR performance. So the OCR was first trained on a real data, but it was fine tuned on this generated data, which was, I mean, something around 70K or 80K images were generated for the OCR. So this was a very recent work. It's done with IIT KGP and it's under submission. So this is like one of the directions that we are exploring. Till now, the data generation, I mean, or the data this thing obtaining process has been mostly manual, but we are moving in these directions also. So now coming to a small problem, but an important problem on semantic search. So what do we mean by semantic search? Which is that given a key, given a text, we don't want to just find that text, but also its related words. So for instance, let's say if I search for taxi, then things like cab, bus, these things should also be searched on device again, right? Or if I search for books, then writing collections, these things should be searched, right? So what are the challenges here? So the challenge is that simple substring search will not suffice, right, because taxi and cab are like totally different strings. So just substring search will not help us get there. And the other thing is now we can use word embeddings, but trying to use the word embeddings directly will be a bit costly. Why? Because just storing these 300 dimensional embeddings of, let's say, only 20K most popular words on device will cost us around 24 MB. And even the computation is like very high. So each every such computation of nearby neighbors of a word using word embeddings, it will require around, in this setting, it will require around 6 million multi-add operations. So these are very costly. So what we try to do is we try to pre-process these computations and we try to build a dictionary. So cab is like similar to taxi and these things, and we try to store this dictionary rather than such these things. So these are like clever tricks that can be done, which uses word embeddings, but on the background it's not used on device. So overall the key learning is that understanding the user scenario is very critical from a ML design perspective. So usually the scenario, what we read in papers in many times, the scenario is like very general, like I need to classify a image or document image even. So even these scenarios become very general when we look from an industrial setting, right? And so there identifying relevant features and what are the constraints, and even defining the model performance and what is the exit criteria, because we cannot work on delta improvement for like even 8 months. We need to fix something and get it over in 3 months. We need to say that it is shippable and it's shipped. Then once in a while some fine tuning is done, but it's not like we have to we can continuously work on it. So even those exit criteria becomes very important while defining ML scenarios. And a major challenge is that the data set may not be available for many scenarios, right? So how to do that? And in summary, AI ML models for mobiles have its own set of nuances, and typically the ML modeling, they are highly influenced by the product which is there. So the M365 product app influenced many of the design decisions that we took in our solutions, and it requires working backwards. We try to understand the model first, I mean the overall end user scenario, and then try to model it. And security and privacy is it's a different topic on its own, but we need to ensure that the sensitive data is protected and it's not shared. And one of the less explored topics is on doing multimodal ML on devices. So I have shown some things on images, some things on text. Now how can we combine these two together on device? That is the main challenge. So with this, I'm concluding that out. Thanks a lot. Yeah. So all those things are fine, but again the challenge becomes on the device side. So can it be done on 300 KB or a 400 KB or a, so all those bigger models, they do very good, very nicely. So the main challenge is the mobile side constraint. So it is definitely doable. There is lot of works which does it in self-supervision, in the self-supervised setting. But I mean the size, the latency, all those things are an issue when you want to do it on mobile. It's not like we capture the data on mobile and then via network we send it to the server, we get it processed and then get it back, because that will then require that the data is leaving user's device, which we don't want to ensure privacy. So everything happens on device. So yes. Sorry, can you speak? Dictionary will take time, space, but it won't be costly. So for example, I can maintain, so using word embeddings, I can create a dictionary that, okay, taxi is similar to cab, is similar to bus, and so this is a very cheap compared to the size and the number of computation that word embeddings require. This is relatively much cheaper. Yeah. So those things are many a times that is decided by the engineering team who will be productionizing the model. So if the engineering team have something which is let's say TensorFlow Lite based, then it will be done on those things. I mean, and if it is let's say PyTorch based, then it will be done on PyTorch. So as of now, we at least we have not seen any specific advantage of one framework over the other. I mean, on the small set of problems that we have explored. But these decisions can change if some framework has an advantage over the other. So it's not a hard and fast thing. Yes. Huh. Huh. Yes, yes. I don't have idea because I mean, one of the main thing is that if you work on, let's say, TensorFlow Lite and all, then it gives a whole API to do certain operations. So let's say the CNN and all are already like an API call, right? If you go into the lower level languages, then you have to build it everything from scratch. So unless there is a business thing which justifies such an investment, such a thing is will perhaps not be taken. Yes. Yes, yes, yes. Huh. So right now, yes. So the API call, yeah. So TensorFlow Lite, for example, we have this thing. The whole thing is there on the device. So all the calls are being taken locally by that. Yes, yes.